Hello, Anthony Fasano here from Pass the PE Exam. In this video, we're going to calculate the necessary source pressure needed to move water through a 3-inch diameter steel pipe by using the Darcy-Weisbach equation and the friction factor diagram provided in the PE Handbook. This question forms part of the Hydraulics and Hydrology section of the PE exam and was created and solved by engineering training Enrique Ivers. This video is brought to you by PPI, a leader in engineering exam prep for the FE and PE exams since 1975. PPI provides expert prep courses and study resources designed to help you pass the PE exam the first time. PPI's live online courses include hours of lectures, problem-solving demonstrations, exam strategy sessions, office hours, and a passing guarantee. When you take a live online course, PPI guarantees you will pass, or you can take the on-demand course for free. With study guides, practice exams, and more, the PPI Learning Hub offers digital practice and review that you can take with you anywhere you have a device so that you can prepare during the times most convenient for you. Check out PPI today at ppi2pass.com to see all the options available for PE exam prep. Let's dive in.
In this problem, we're asked to find how much the gauge pressure should be at the water source to meet a specified pressure and capacity over a certain distance and elevation gain. The problem reads, the distance from the basin to the facility is 500 feet, and the facility is at an elevation 25 feet higher than the basin. The specified capacity is 100 GPM, gallons per minute, with at least 20 psi of pressure at the gauge at the facility. If a 3-inch internal diameter steel pipe is used, how much pressure needs to be provided at the basin in gauge psi? The Reynolds number is determined to be 2 times 10 to the 5th power, and the specific roughness per the pipe manufacturer is 0.0002 feet. We're then asked to choose which gauge pressure is closest to the required pressure to meet those specified requirements. A, 14 gauge psi, B, 25 gauge psi, C, 36 gauge psi, and D, 47 gauge psi. So before we start annotating the key information of this problem, we should be able to eliminate one of these potential answers with just a little bit of critical thinking. So we're told that the required pressure at the end of the pipe where the facility is 20 psi at the gauge. And we know that there is going to be extra force required to pump the water up 25 feet. We're told there's an elevation of 25 feet. And of course, there are going to be friction losses as well. So right off the bat, we know that 14 gauge psi does not exceed 20 gauge psi. So answer A is immediately off the table. We don't know for certain whether answer B is within the realm of possibility or not, but if I were to do calculations and get that answer, I would probably end up checking my work just to make sure. So having eliminated one of those 4 answers, we can now actually get started on this problem, and we should start by doing so by annotating the key information. So first, the total length of the pipe is 500 feet. We can assume that this includes the amount of pipe required for that 25-foot elevation gain, and we will call this L. Second, the elevation difference, the elevation gain between the source and the destination is 25 feet, positive 25, and we will call this delta H. The specified capacity of the pipe is 100 gallons per minute, and we will call this Q. The pressure at the facility needs to be 20 gauge psi, and we're told that the pipe is made out of steel and it is 3 inches in internal diameter. Finally, we're given 2 crucial pieces of information. First, the Reynolds number is 2 times 10 to the 5th power. Now, recall that anything less than a Reynolds number of 2000 falls within laminar flow, and anything above 4000 is turbulent flow. Accordingly, 2 times 10 to the 5th is well within the range for turbulent flow. So this will dictate the equation that we use to solve this problem, but we'll get to that in a little bit. We're also told a couple other pieces of crucial information. The pipe-specific roughness, lowercase epsilon, is 0.0002 feet. We're given this in the problem statement, but if we were not given this information, we would have to use the PE Handbook to look up the table for specific roughness and find what that typical value is for steel pipe and use that as our assumed value. But since it's given to us, we don't need to do that. So the question asks for the necessary pressure at the basin in gauge PSI, and we should calculate the equivalent total head of the system in feet and then convert it back to PSI. We know that due to the conservation of energy, the pressure and the head in the system needs to be balanced. So we have inequalities that we can set up to reflect this. We can write that the head at the basin, which is the source, H sub PB, is equal to the head at the facility, H sub PF, which is given to us as a specification requirement, plus the head associated with the elevation gain, delta H, and lastly, the head loss due to friction caused by traversing 500 feet of steel pipe, which we will call H sub F. For H sub PF, again, we substitute in our 20 gauge PSI, and we do have to convert PSI to feet of head, and the conversion factor is 2.31 feet per PSI. We also know delta H, this is already in feet, and that is our 25-foot elevation difference. As of yet, we don't know what our friction head loss is, and this is going to be the main challenge in solving this problem. There are a number of equations that we could use to solve to find the friction head loss. We are given some constraints in this problem, though. We're told that the flow is turbulent and fully developed by the Reynolds number, since it's greater than 4,000. Since we're talking about fully developed turbulent flow, we should use the Darcy-Weisbach equation to calculate the friction head loss. Note that in this type of problem, especially since we're told we're dealing with water, we can assume that it is steady state and incompressible. Using the Darcy-Weisbach equation, H sub F is equal to the product of the numerator, which consists of the friction factor F, the length of the pipe, the velocity of the flow squared, divided by the product of the denominator, which is 2 times the diameter of the pipe times the gravitational constant. F, the friction factor, is found in the PE Handbook within the Moody, Darcy, or Stanton friction factor diagram. We'll cover how to reference this diagram in a moment. As aforementioned, L is the length of the pipe, V is the velocity of the pipe. We should understand this to be the volume divided by the cross-sectional area of the pipe. D is the diameter of the pipe. Note that in the Darcy-Weisbach equation, the units for this are in feet, not inches, so be very careful here. G is our gravitational constant, so make sure to use the correct constant for the units used in this problem. And going back to the Moody, Darcy, or Stanton friction factor diagram, which is provided in the PE Handbook in version 1.1, this is on page 312, we note that the axis on the right, the vertical axis, is labeled relative roughness, which is lowercase epsilon divided by d. Lowercase roughness, the specific roughness, was given to be 0.0002 feet in the problem statement, and the diameter of the pipe is 3 inches, or 0.25 feet. So to find the relative roughness, we need to take the quotient of the two, and we find that to be 0.0008. We identify the curve for a relative roughness of 0.0008. You may have to extrapolate a little bit if the problem you're working on doesn't line up perfectly like this one does, although if it doesn't, it would probably behoove you to recheck your calculations. This typically isn't something that they're going to try to trick you on. So identifying that curve, we move to find the position on the x-axis corresponding to a Reynolds number of 2 times 10 to the 5th. Finding that point of intersection gives us the corresponding friction factor F, approximately 0.02. Now, as we recalled earlier, V is the volume of flow divided by the cross-sectional area. V equals Q over A. When we substitute our values into the equation, 100 GPM for Q and 1.5 inches for R, recall that the diameter of the pipe is 3 inches, so the radius is 1.5. We need to convert that radius of the pipe from inches to feet. So continuing to simplify and incorporating our conversion factor of 449 gallons per minute per cubic foot per second. Again, this is why we had to convert from inches to feet for the radius of the pipe. We find that the velocity of the flow to be 4.536 feet per second. We now have everything we need to solve for the friction head loss with the Darcy-Weisbach equation. For the friction factor F, we substitute in 0.02, and we substitute in 4.536 feet per second for the velocity. Note that when we use the gravitational constant of 32 feet per second squared, we make sure to use the appropriate gravitational constant. Make sure that you don't absent-mindedly use the constant for metric units. Simplifying the equation, we find that the friction head loss is 12.78 feet. This was the final unknown in our balanced hydraulic head equation that we first started with. So now we can substitute in our 12.78 feet. We simplify and we find that the head at the basin needs to be 83.98 feet. We still have a couple steps though. We need to convert back to PSI to correspond to the gauge PSI listed in the potential answers. So using our conversion factor, the inverse of what we used initially, 1 psi per 2.31 foot of head, we find that the pressure at the basin must be a minimum of 36.4 gauge psi. Referencing our provided options, we see that this is closest to answer C, 36 gauge psi.
I hope you found this week's video helpful. In upcoming videos, we will solve more PE exam practice problems and answer other questions from our subscribers. Pass the PE exam videos will be published weekly, so please be sure to click that subscribe button so you don't miss something that could make a substantial difference in your PE exam result. This exam means everything to your career. And please, ask questions and leave comments below this video and I will respond to you. Let me know if there's a specific topic you'd like me to cover or a question that you need answered. Pass the PE exam, we'll have you covered. I'll see you next week on Pass the PE exam.